Hello, my name is Sylvain Allais from Université du Québec à Chicoutimi in Canada, and in the next few minutes I'm going to talk about a solution we implemented to address the issue of user interface bugs related to responsive web applications. This work has been realized with my fellow students Francis and Usama, and is a follow-up on an earlier work dealing with layout bugs in general. Before going further, let us first recall what is responsive web design. To illustrate this principle, we take as an example a classical web page that contains a few menu items, a form, and a couple of buttons. In a large screen such as the one you typically have on your computer, the page uses most of the viewport to display the top menu as a horizontal sequence of items. The sign-in form is centered with the social media buttons at the right. If the user's screen is slightly narrower, these elements will shrink a little so that their proportions fit the available space. However, on very small screens, such as smartphones, that space is insufficient to properly display all the elements in their original disposition. To address this problem, a responsive website will rearrange, resize, or even remove elements of the page. The design is different and is adapted to the size of the screen. All these shufflings and displacements are typically done on the fly each time the viewport is resized and use a mix of client-side code and CSS media queries. In a way, this can be seen as a more elaborate version of the so-called fluid design that websites have been using for decades, but with a much more increased capacity to change the structure of the page. However, correctly programming a responsive web layout is a delicate task. After all, one must provide a way to decide what elements to show and where for all possible page sizes. This may sometimes result in corner cases that are not correctly addressed. For example, this screenshot shows the same web page as before, but in a window whose white is a middle ground between, say, a small telephone and a large computer screen. One can easily see that this layout is probably not what the designer intended. There are horizontal and vertical scroll bars, the sign-in form is not centered in the page, and some menu items are not directly visible. Ladies and gentlemen, I present you the responsive web design bug. This next screenshot shows that these kinds of problems can occur on many different occasions and create a wide range of problems that are not just related to aesthetics. In this example, the box text is flatly unreadable and scroll bars don't even help. Some cases are more subtle, but are still responsive bugs nonetheless. In this last example, the menu at the bottom fits on one line in the first picture, but breaks into two lines if we slightly reduce the size of the window. One could argue that this may be the intended behavior, except for the fact that the items shrink and return on the same line if we further reduce the window. A recent work by Walsh and friends classified responsive bugs into 5 categories. First, element collision occurs when two rectangles on the page overlap for some viewport sizes, while they don't the majority of the time. Element and viewport protrusion occur when some element suddenly expands outside its parent container. Wrapping elements is exactly the examples we've just seen, where menu items broke on multiple lines. And finally, small range layouts correspond to some types of layouts that exist only for a very narrow interval of viewport sizes, typically a few pixels. Based on all these observations, the obvious question becomes, how can we detect such bugs? A possible solution is to perform manual testing, and as a matter of fact, is the solution generally used in a web development context. However, this approach has a few downsides, the most important being that it is extremely slow. In order to catch bugs, one would need to check all viewport sizes for all pages of a site every time the design is modified, which is obviously infeasible. A second and probably better solution is to try to automate the process. That is, trying to come up with some systematic rules that could be evaluated to detect the presence of layout bugs. But now our problem has been transferred to defining these rules in the first place. This, in a nutshell, is the problem we attempt to solve in this contribution. Here's an overview of our proposed solution. First, our setup involves a piece of software called the driver, whose purpose is to interact with the web browser instance. Although a driver could be used to perform various actions in a web page, in our solution the driver is solely used to resize the window progressively. That is, the driver will first load a page at some width W1 and wait a little. Then the driver will set the viewport to a slightly smaller width W2 and wait a little more. After a while, the driver will yet again resize the page to a smaller size and so on. Each time the page is resized, a probe injected into the page will retrieve data about the elements it contains, such as their dimensions and relative position. This will create a sequence of page snapshots, but beware, the snapshots are not pictures but rather small data structures such as JSON. Finally, a test oracle will be given the sequence of snapshots and be asked to evaluate some formal property on it. We call the oracle stateful in the sense that its job is to correlate the state of different snapshots and highlight relevant differences between them. In the end, responsive bugs become conditions on sequences of page snapshots that the probe, with the help of the driver, produces in real time. This might be reminiscent to some of linear temporal logic, which is a formal language designed specifically to express constraints on sequences of events. As a matter of fact, our proposed architecture can be seen as a form of runtime verification. In this setting, a system is being observed by a kind of camera which we call the instrumentation, and this instrumentation produces a sequence or trace of data elements called events. The observer in this example corresponds to our stateful test oracle. Concretely, our bug detection framework is made from the combination of two existing components. The first is crawljax, a Java software tool that can automatically crawl a website and evaluate conditions on each visited page. This will serve as our driver. The second is CornyPickle, a tool that our own team developed and which is used in the form of a plugin inside crawljax. Crawljax is relatively well known, but what exactly is this CornyPickle? Well, the system is itself made of three main elements. The first is a language to express high-level constraints on web interfaces. It allows a user to write statements that refer to a DOM tree and CSS attributes. It has support for first-order quantification and the famous temporal operators I've talked about just a minute ago. The second component is an architecture to instrument a web application and report relevant attributes to an interpreter. This is the probe injected into the pages in the form of a snippet of JavaScript. Finally, the third component is an interpreter that can verify properties on snapshots provided by the probe and also explain why the properties are violated in the case this occurs. CornyPickle uses a language that is designed to look a lot like English in order to make properties readable to non-specialists. For example, quantifiers such as for each and there exists, which allow to express conditions on a set of elements picked by some CSS selector, are written, well, exactly like that. The language also provides ways of accessing an element's various properties, compare values or match a string, all in a relatively straightforward syntax. Conditions can also be combined using the common Boolean connectives, and constraints on sequences of snapshots can be written using LTL temporal operators. Unfortunately, we won't have time to go into the fine details of the semantics of these operators, but I think their intuitive meaning is clear. Finally, one of the most important parts of our approach is that a user can define a kind of macro when the language does not directly provide a way to write a condition. This is done using a construct called WeSayThat, which can map a pattern expression to an underlying lower-level statement. Macros can also contain macros themselves, which means that one can progressively build a language of high-level constructs specific to particular situations. If you read the paper, and I hope you will, you'll see that in the present case, we build a vocabulary of concepts that can express topological relationships between elements, such as what it means for two elements to overlap, or for one to be fully contained within another, etc. Equipped with such a vocabulary, The 5 types of responsive bugs defined by Walsh can now be expressed as high-level corny-pickle properties. This first example shows what element collision looks like when written as a formal constraint. Glossing over the details, we can still understand that this property stipulates that 2 elements that do not overlap in a page snapshot should not overlap in any future snapshot. Element protrusion works in a similar way and stipulates that if 2 elements are such that one is contained within another, they should remain so for every page snapshot. And as a last example, the wrapping elements property, when applied to a list, says that if the list is aligned in a snapshot, it should also be aligned in the next snapshot. So this property gives an example of the use of predicates by defining the expression "the list is aligned" on the left, and then reusing it in the condition on the right. An interesting feature of this approach is that responsive bugs are now formal properties in a generic and declarative language. Since they are not hard-coded conditions, this means that new types of bugs could easily be accommodated into the system by writing the corresponding statements. In addition, the interpreter can not only identify but also highlight in the page the faulty elements that cause a condition to break. The picture below shows an actual example of such highlighting, which points to 2 menu elements that are very slightly misaligned. So now the question is, does this thing scale? We made a couple of measurements. First, by increasing the size of the page and measuring the time it takes to evaluate all bug conditions. The good news is that for pages of 500 elements, it takes less than 25 milliseconds to check if a page snapshot is okay. The hardest part is actually on the probe side, which is written in JavaScript. Our experiments show that this probe takes quite some time to serialize the content of a page and produce a JSON element with it. It's up to 60 seconds for a page of 500 elements. This is clearly the bottleneck that would need to be addressed in future improvements of our solution. Nevertheless, let us not forget that this tool is intended to be used at the step of development, not to run online on production pages. In such a context, we can probably afford to wait a little more, and besides, 1 minute of processing time is not all that bad if the system can help us catch subtle bugs in return. I shall end by saying that our solution is open source and freely available, and also that we are currently working with a Canadian web design company to try to integrate our plugin somewhere in their production pipeline. Alright, thank you for your attention, and I encourage you to visit our lab's website or my personal webpage for more information about this and other tools we work on. Thank you.